Isentropic flow with area change. By combining the isentropic and or adiabatic flow, and or adiabatic flow relation with the equation of continuity, we can study practical compressible flow problems. This section treats the one-dimensional flow approximations. Consider this figure for more descriptions. This figure illustrates one-dimensional flow assumption. A real flow was shown in the part A, real flow and real velocity profile, has no slip at the walls, and a velocity profile B, x1 as shown here, and no slip conditions here, that varies across the dog section. If, however, the area change is small and the wall radius of curvature large, we have this relation for part A, the real flow with we had two-dimension variable. We have for the enthalpy change in x direction is too small, and excuse me, it is not enthalpy, it is the distance between two plates hx, and we know that also hx is smaller than the rx. Then the flow is approximately one-dimensional as shown in the part B in this picture, and we can assume that so what we have is the approximately one dimension. Compressible flow nozzles and diffusers do not always satisfy conditions in the previous relation here, but we use the one-dimensional theory anyway because of its simplicity. For a steady one-dimensional flow, the equation of continuity, we know that for the equation of continuity, m dot rho v a, or we have and ax, m dot and is constant. Before applying this to the dog theory, we can learn a lot from different form of the equation, which was d with the derivation we can obtain this. This relation obtained from this rho VA equals to 0, which can obtain it with derivation on each part of this expression. We have rho A dV and rho V dA. We divide into rho VA, we can obtain this relation for a continuity equation. The differential form of the frictionless momentum equations and the sound speed relations are recalled here for convenience. Let me write again here. For continuity we have this relation dV on A, dV on V, and dA on A equals to 0 momentum, and for the continuity, and for momentum we had this relation on rho and also we have a relation for the speed of sound, which was A square dP on d rho, or dP equals to A square d rho, speed of sound. Now eliminating dP and d rho from these three equations, we can obtain the following real relations. dP and d rho, we have also dP here, it is rho. We can obtain the dV on V, dA on A, multiply to a expression of a function of Mach number, which is also equals to dP on rho V square. Inspection of this equation without actually solving it reveals a fascinating aspect of compressible flow. Property change are of opposite sign for the subsonic. Let me write them. The one specification of this relationship say that property change are of opposite sign for subsonic and supersonic flow because of the term property change are of opposite sign for subsonic and supersonic flow because of the term of Mach number -1. There are four combinations of area change and Mach number for combination area and maximum. Shown in, let me provide a picture for more description. For combination of Mach number and area as this picture. As shown in this picture, we have subsonic, Mach smaller than 1. For duct geometry, we have two different duct geometry. If the area is increasing, we say that dA greater than 0. For the subsonic condition, and considering this equation, dA on A if dA greater than 1 and Mach greater smaller than this, for the subsonic this constant is smaller than 0. So for dA greater than 0, we have dV equal dV smaller than 0, and also it is equals to minus dP on rho V2. In this case, dP greater than 1, greater than 0 for the subsonic, and for supersonic, and for the, let me write here, for supersonic we have a positive sign here. So if dA greater than 0, we have also dV equals greater than 0 and dP smaller than 0. So this is a nozzle subsonic diffuser. And it is supersonic nozzle because the pressure decreases during this flow. For the another case, we have another geometry here. If we had dA smaller than 1, subsonic and supersonic. For the subsonic, we have this term is smaller than 0. So if dA smaller than 0, we can obtain dV and dP dV and dP always have the opposite sign. This is a nozzle, subsonic nozzle. And for the supersonic, the Mach number greater than 1. This expression is positive. So if dA smaller than 0, dV also smaller than 0, and opposite we have dP smaller greater than 0. This is the diffuser. What about the sonic point? The point is where the Mach equals to 1. Since infinite acceleration is physically impossible, indicated that dV can be finite only when dA equals to 0. We have this relation. On rho V2. The Mach number, a sonic point which Mach equals to 1, we have a singularity point here, so if dA equals to 0, we have the dV can be finite only. A minimum area or a maximum area can be supposed as this picture. Consider this picture for more description. In this picture, we patch together a truth section and a bolt section as shown here. Truth section and bolt section. Using the rules in the previous description for area change and this relation. And first it is dA, and in this area we have dA greater than 1. We have a minimum of area here. The truth or converting diverging section can smoothly accelerate a subsonic flow through sonic to supersonic flow, as this picture shows. This is the only way a supersonic flow can be created by expanding the gas from a stagnant reservoir. The bolt section fails. The bolt Mach number moves away from a sonic condition rather than toward it. Although supersonic flow downstream of a nozzle requires a sonic truth, the opposite is not true. A compressible gas can pass through a truth section without becoming sonic. In this case A, we can have a sonic flow during diverging and converging, diverging, section. And then the second one, A compressible gas can pass through a through section without becoming solid.